So today we are finally going to get to define the derivative, which is going to be what we'll basically spend the rest of the semester discussing. Or, well, not just the derivative, but we'll be discussing implications of it as well. And if you've been following along so far, you probably have some idea where I am going with this, but I want to make sure to make this really, really precise. So here is what we're trying to do. We want to talk about the instantaneous rate of change. And the idea behind this is we understand how to find the average rate of change. To find the average from A to B, what do we do? If I have some function f, I use the following formula. I have f of b minus f of a divided by b minus a. Also, what I have is a really terrible pen. I don't know how this happens to me so frequently, but let's see if maybe this one is a little better. So this is my average rate of change over the interval from A to B. That's fine. This is also the slope of the secant line. Again, that's fine. We know how to deal with that stuff from before. But now that we have access to the notion of a limit, we are finally going to be able to ask ourselves, what happens as B gets closer and closer to A? So we will define the rate of change at x equals A. This is going to be the limit as B approaches A of f of B minus f of A divided by B minus A, if it exists. So there we go. There is our formula. And this is also called the derivative of f at A. Now, we should make sure that this definition really does make sense. I mean, intuitively, it's kind of like, what else could we possibly do? But we want to make sure that this does in fact make sense in some particular cases. So let's take a quick look at some examples of this sort of thing and make sure that it really does seem like it's working out the way that we would expect. So, for example, if I want to find the derivative of f of x equals 3 at x equals 4, well, we would expect, because this is a constant function, its rate of change should always be 0. Think about what a constant function does. It never changes. Its change is always 0. So we would expect that its rate of change would always be 0. But that is, in fact, going to be the case, because what we're going to be doing is we will be looking at the limit as b approaches 4 of f of b minus f of 4 divided by b minus 4. But this is actually the limit as b approaches 4 of 3 minus 3 over b minus 4. And now, the thing to observe here is that this numerator is always 0. 3 minus 3 is always 0. And because we can just change a fraction by canceling things in the numerator and the denominator without changing the limit, since this is the limit as b approaches 4 of 0 over b minus 4, this is actually just the limit as b approaches 4 of 0, which is 0. That was a very lengthy way of showing that, this limit is in fact 0 by the limit laws. You could probably see it directly from here even, that we skip down to the end, it's going to come out to be 0. But this is exactly what we would expect. We would expect that a constant function would have a rate of change of 0 everywhere. So in particular, we verified it has a rate of change of 0 at x is equal to 4. So let's take a look now at another example of doing this kind of thing. And let's suppose that we want to find the derivative of, let's say, g of x is equal to 3x plus 1 at x equals minus 1. Before we find that derivative, we are going to find a working pen, I swear. Something around here has got to actually be a functional pen. There, finally. Okay, so let's think about this example. Well, this is going to be the limit as b approaches negative 1 of g of b minus g of negative 1 divided by b minus negative 1. This is going to be the limit as b approaches negative 1. Now the denominator, let's simplify that really quick because we can do that fairly simply. This just turns into b plus 1. And in the numerator, we're going to have 3b plus 1 minus 3 times minus 1 plus 1. So this becomes the limit as b approaches negative 1 of 3b plus, now let's count this carefully. This is negative 3 plus 1 is negative 2, but we're subtracting it. And 1 plus 2 is 3. So we get 3b plus 3 divided by b plus 1. Make sure that you follow exactly where I got that 3 from. It's just from simplifying out all of these constants, okay? So take a moment, make sure that you're okay with that, and then let's keep going here and see what we can get. This becomes the limit as b approaches negative 1 of 3 times b plus 1 over b plus 1. The b plus 1s can cancel though, and now this is just the limit of a constant, so this comes out to be 3. This is actually exactly what we would expect. So think about why we would expect this. This is a linear function, right? 3x plus 1, that is linear. What is the thing about linear functions? Well, they always have the same average rate of change. They always have the same slope. Like there is one fixed slope between any 2 points on a line. That's kind of why we call them linear functions, because they follow a straight line. Well, if that's always the average rate of change, the average rate of change here would be the slope, which is 3. The instantaneous rate of change, we would expect that to also be 3. It doesn't make sense that the average would always be 3 if at some points the actual instantaneous rate of change were something different. In fact, later on, we will see from a very special theorem called the mean value theorem, we can make that notion precise. We can say, yeah, if, like, essentially that would be impossible to have that happen any other way. But for now, just notice, from this computation, we get 3, and that's really intuitively what we would expect, because this is a line with a slope of 3. Now, I want to notice something here about this derivative that we have defined. The thing that I would like to notice is this. We wrote it as the limit as b approaches a, f of b minus f of a divided by b minus a. This is not always the most convenient way to write this. A slightly more convenient way to write this sometimes is we write x equals a, and we write b as x plus h, which is the same thing as saying that h is equal to b minus x. Now, what happens if we make these substitutions? Well, in that case, what we're doing is we're taking the limit really as h approaches 0, because if x is a, then b approaching x or b approaching a, that really just means that this h term is vanishing to 0. And b is x plus h, so this is f of x plus h minus f of x, because I'm rewriting the a as an x, and then b minus a. Well, b minus a is actually just x plus h minus x, which is just equal to h. So this is another way of writing out the derivative at some point x. And sometimes this is a little bit more convenient to work with, okay? So let's take a quick look at an example where, in my opinion, this is a slightly more convenient one to work with, although you can always do this with either of them. It's just that some problems are a little bit easier to do with one format than the other. And so I don't want you to feel like one format is better than the other or worse than the other in general. Usually I tend to prefer this form on the right. I usually think that's a little bit easier to work with, but occasionally the one on the left is nice to work with too. So let's take a look at an example of using the derivative rewritten in this form. Let's suppose that we want to find the derivative of f of x is equal to x squared at 2. So the way that we're going to do this is we're going to take the limit as h approaches 0, f of 2 plus h, because we're doing this at 2, minus f of 2, all divided by h. So you can see here where we're doing this at 2, so I replaced these with 2's, and then we're just taking the limit as h goes to 0. So let's see if we can plug this in and what that's going to give us. Limit as h goes to 0, then we're going to have 2 plus h squared minus 2 squared, all divided by h. Okay, now we have to simplify this out. Now here's where things are going to get not super messy, but they might get a little long. We have to expand this using the formula for perfect squares. This is going to give me limit as h approaches 0, 4 plus 4h plus h squared minus 4, all divided by h. Now, the 4's cancel, and this leaves me with the limit as h approaches 0 of 4h plus h squared divided by h. But you'll notice now that I can factor out an h. And in fact, let's rewrite this up at the top because I am running out of space here. So this is going to be the limit as h approaches 0 of h times 4h. What am I doing? I'm factoring out the h, so that h is gone. 4 plus h divided by h. Well, the h's now cancel. What is left is a polynomial in h, so I can find this by evaluation. I just substitute in h equals 0, and I end up with 4. Now this is very interesting because what it tells me is that if I were to look at the graph of x squared, y equals x squared, what I end up with here is this parabola, and it tells me that at this point, the slope, the rate at which this curve is changing, is going to be equal to a slope of 4. And that's a kind of an interesting thing. That is the rate at which this parabola is changing instantaneously when x is equal to 2. And that is what this derivative technique allows us to find. Now, historically, people were very interested in this kind of thing because finding rates of change like this is a really important question in a lot of cases. For instance, if we're talking about physical motion, then the rate at which position is changing is your velocity. So if we can measure where something is, can we talk about its velocity? It's easy to talk about average velocities because we just measure the difference in positions divided by the difference in times. But to calculate the instantaneous velocity, you need methods like this. And that was a big reason why Newton got, into this kind of thing. And of course, other people were studying this stuff too. Leibniz, for example, who we'll be mentioning him again later, he was studying these kinds of things for similar reasons. Neither of them were really the first to think about this stuff. People were thinking about this stuff before then as well. But, that's what motivated people to look into these kinds of definitions. The key thing was that they needed what is the notion of a limit. Now, I will note, historically, this is a bit of a historical digression here, but historically, Newton and Leibniz did not have access to the full definition of a limit. Instead, they just kind of had the intuitive idea of a limit, and the way that they did it was actually, Newton, for example, he sometimes talked about these things as infinitesimals. So he thought about, essentially, he was like, well, whenever I feel like it, I can throw out my h's at the end of this process. Justifying throwing them out required this precise definition of a limit that we had, and it turns out Newton's rules for getting rid of his h's are just the basic limit laws. For him, he just kind of thought of them intuitively and then used the results. He didn't worry about whether this was fully justifiable from a rigorous perspective. So it was later on that we brought sort of a precise definition and made sure that everything here really does work out and make sense. But he was able to do this because he had an idea of what limit laws should be. And, the fact that, for instance, when you're doing a limit of a polynomial, you should just be able to do it by evaluation, essentially. He had that kind of idea, and so he was able to work with this stuff. Now, I want to mention how this plays a role into the geometry. So, given a curve, and excuse me while I write this down, given a curve y equals f of x, the tangent line at x equals a is the line that goes through the point a comma f of a with slope given by the derivative of f at a. So you can think of the tangent line as actually the limit of the secant lines in a very precise sense. It really is the limit of the secant line. So if you take some curve here, y equals f of x, and you have some point A, we can talk about the various secant lines that go through this thing, like so, or here's another secant line. The tangent line is going to be the line which has the same slope as the curve does at this point. It's very difficult to see with all these extra secant lines thrown in there. But so the tangent line is going to be the line which just touches the curve going in the same direction. And here's a good way to intuitively think about this. Imagine that this curve, f of x, is actually imagine that this plane is a field, like on the ground, or it's on the floor. If I'm walking along the curve f of x, the tangent line is the line along which I'm looking as I walk this curve as I pass through this point. Remember, this is going to be the point a comma f of a. Well, as I pass through that point, I ask myself, what direction am I actually looking? I'm looking along some straight line. The tangent line is going to be that line. And for most curves, that means that the tangent line touches the curve at exactly one point, at least on some open interval around A. There's exceptions, like straight lines, you just keep on top of the curve the whole time. But generally speaking, the tangent is going to be one that just touches the curve at that one point. Now, of course, later on, the curve might turn around and my tangent line might cut through it. But in some open interval near A, I just barely tap the curve at this one point, and that's it. So, how do we find tangent lines? Well, in general, we find the tangent lines by just calculating the derivative and then figuring out what point to go through, because then we can use point-slope form in order to find the tangent line. So let's do the following example. Let's find the tangent line to y equals 1 over x when x is equal to, let's say -2. Okay, well, at this point, the point is going to be -2 comma 1 over -2, which is actually -2 comma -1/2. Okay, so that's the point this thing is going through. Well, now we need to find the slope. How are we going to find the slope? Well, I'm going to go back to using the limit as b approaches -2 of 1 over b minus 1 over -2 divided by b minus -2. So I have gone back to the AB definition here. We could do it with the H's as well. And I will leave it to you guys to kind of think through how you could do this with the H's definition. Now, what am I going to do at this point? Well, we can do a bit of simplification, because this is a complex fraction, right? And we're used to simplifying complex fractions. Or maybe we used to be used to them, and maybe you haven't done it for a while. But if I take a common denominator up here, I first have the limit as b approaches -2, and then I multiply. Actually, let me rewrite this like so. 1 over b plus 1/2 divided by b plus 2. That gets rid of some of our negative signs and things. And then I can say, okay, so this is actually equal to, if I multiply on the top and bottom over here by 2, I still have limit as b approaches -2, and then I'm going to have 2 plus b divided by 2b, all divided by b plus 2. Now, the b plus 2's cancel, and this becomes the limit as b approaches -2 of 1 over 2b, which I can now do this by evaluation, because this is a rational function in terms of b, and the denominator isn't 0 if I plug in -2. So this becomes -1/4. This tells me that the slope here is -1/4. Now, if you make a graph of what 1 over x looks like near -2, this actually makes a lot of sense, because think about what this curve looks like. It looks something like this. So yeah, if I were walking along this, it looks pretty reasonable that I would be going downwards with a slope of about -1/4. I mean, you can't tell just by eyeballing it exactly what it's going to be, but it does look like that's the direction that I would be facing, right? So it's actually kind of, I'm not going to say, like, you can't see it by eyeballing again, right? But it's plausible. That's the word I'm looking for. This answer definitely makes sense. If I had gotten an answer that was like, let's say, a positive number, that wouldn't make a lot of sense, because it looks to me like I should be coming downwards here. The tangent line should definitely be having a negative slope. But this is negative, so that's good. It also shouldn't be a big negative number, though, because the curve is not very steep here. So because it's not very steep, I expect it to be a kind of a smallish negative number. And that's exactly what we've gotten, a smallish negative number. So although that doesn't tell me for sure I've done this correctly, it does tell me my answer is reasonable. And that's an important thing, right? We want to make sure our answers are reasonable. We want to be able to at least recognize if we have an answer that is completely ridiculous seeming. Like, you get an answer of 5 billion here, that's probably incorrect. Okay, so now I have my slope calculated. And I have my point. So all that remains is to use point-slope form to write down my tangent line. So we're going to have y plus 1/2 is equal to -1/4 times x plus 2. And there is my tangent line. I could, of course, rewrite this in terms of, I can rewrite this in slope-intercept form if I want to, but often writing a tangent line in point slope form is perfectly fine. And then if you need to convert it into a different format, you go ahead and you do that. You know, whatever you need from that point, you're just working with standard lines. So there we go. That's how you calculate the tangent line to something. Now, a couple of notes here that I want to make. First note, one of the things that a lot of students do when they're working with limits is they start dropping limits. Like, you start writing this and you kind of forget to write in that this is still the limit as b approaches -2. This is still the limit as b approaches -2. Because the thing is, you know in your head what you're doing, and it's so much extra work to have to keep writing this out, so much extra space. The temptation is to stop writing out limit as b approaches -2. I'm going to warn you, keep writing it until you are actually taking the limit. So until this step, I need to continue having limit as b approaches -2. It is wrong to just drop that limit thing prematurely, so to speak. You may know what you're doing. There's two problems with it. First of all, you may know what you're doing, but somebody else looking at your work doesn't. So they're going to say, wait a second, you've still got b's. How could you have taken the limit? Like, if you've gotten rid of the limit symbol, then it means you've already taken the limit, but there's still b's. Those shouldn't be there anymore after I've taken a limit. The other problem with it is, even for you, if you start dropping your limits and then you forget exactly what you're doing, how are you going to go back and figure it out? You're going to have to go all the way back to figuring out, where was the last place we had a limit. Now, I'm not saying it's that hard, but to be correct, we need to keep on with this limit symbol until I actually take the limit. So, don't drop your limits. That's kind of where I'm going here. Don't get rid of the limit symbol until you've really taken the limit. There was another point that I wanted to get. Oh yes, the other point that I wanted to get to was, let's talk a little bit about these tangent lines and visualizing tangent lines and what would be reasonable for a tangent line. So for example, if I give you a curve like this, and I ask you if you can estimate the tangent line, like let's say here is my curve, y equals f of x, and let's say that I ask you to estimate the tangent line at x equals 1. Or actually, let's just estimate the tangent's slope at x equals 1. Well, what I can do is I can say the tangent line should go in the same direction as the curve. And when I look at this, this looks to me like it's definitely got a downward slope here, right? So we expect the tangent to be a negative. And it also looks like it's sloping down sort of quickly, but not super quickly. Like if I look at this thing, it looks like the rise over run is about -1 down when I move over by maybe about 1. So it looks like this would be approximately a slope of -1. It might be a little smaller. It might be more like a slope of, say, -2/3, but it's definitely somewhere in that general vicinity. Like, again, we're eyeballing this, so you can't come out with an exact number. But we can definitely come up with, reasonably, I expect the slope to be approximately -1, maybe a hair smaller, probably not any big, probably not a larger negative number, bigger magnitude. Not, because technically if it's a bigger negative number, then it's actually less than. But what I mean is the magnitude should be somewhere between 2/3 and 1 or in that region, and it should be negative. Now, if I wanted you to then estimate the tangent slope at -1, what do you think this looks like it comes out to be? Take a minute to kind of eyeball that and see what you can say. Okay, so to me, I look at this thing, and this looks to me like it's definitely going to be positive, and it looks to me like as we move over by 1, I go up by about 1/2. So the slope is probably approximately positive 1/2 at that point. Again, I'm really just estimating this. I don't have a formula here for f of x. all I have is this sort of drawing of it. I have this graph, but that's all I've got. However, what I can say is, yeah, it looks to me like the slope is approximately 1/2. So if you're just given a graph and asked to estimate the derivative or estimate the slope of the tangent line, remembering that those are really the same thing, you can do that by just kind of eyeballing the graph. You take a look at it, you ask what reasonably seems like the tangent line here, and what kind of slope would you have? And that kind of gives you your answer. Similarly, if I, were to say, somebody does a calculation and they found that the tangent line at -1 has a slope of -15. Well, you could look at this and you could say, well, -15, that would be a line that goes like this. That is clearly incorrect. It does touch the curve at exactly one point, but it's not a tangent line because it's not the direction we would be facing as we walk along this curve. And so that is really the key definition to the tangent line. It is the direction you are facing as you walk along the curve through that point of the curve, so to speak. That's sort of my intuitive way of thinking about this. Well, a line that cuts across your curve doesn't satisfy that. So if somebody tells me this has a slope of -15 here, I'm going to tell them, no, that is clearly incorrect. Something has gone terribly wrong with your calculation because I'm looking at this curve and I don't know exactly what the tangent is, but it's a relatively moderately small positive number. It is definitely not a big negative number here. All right, so that gives us the definition of the tangent at a point. What we're going to cover in our next lecture is how actually it gives us the derivative at a point, which also gives us the slope of a tangent line. What we will cover in the next lecture is how actually the derivative defines a function in its own right. And how can we kind of write down what that function is in general? Given some function, how do we write down the derivative as a function? So we will be thinking about the derivative as a function, and then what we'll want to do is we'll want to say, okay, so can we use that derivative as a function to then do things like calculate a bunch of tangent lines very, very quickly? The answer is yes, because once I know the derivative as a function, I can just start evaluating that at different points to get the slopes of different tangent lines. And after that, what we're really going towards here is eventually we're going to kind of work out what are some rules for derivatives that will make it perhaps easier to calculate what the derivative is without always having to go back and explicitly calculate a limit using the limit laws. So I will leave you with one more quick sort of exercise to think about here. What is the derivative of x cubed at x equals 0? Take a minute to think about this, and then we'll work it out together. Okay, so how do I do this? Well, I'm going to do this using the h's definition. So the limit as h goes to 0 of 0 plus h cubed minus 0 cubed divided by h. Well, this is equal to the limit as h goes to 0 of h cubed minus 3 times h squared times 0. I don't have room here. Give me a minute to write this out below. This is going to be where having this tiny whiteboard is going to drive me absolutely nuts, because some of these things we're going to do are going to be pretty long. So we're going to have, actually, let me write it this way. The limit as h goes to 0, 0 cubed plus 3 times 0 squared plus h plus 3 times 0 times h squared plus h cubed minus 0 cubed, all divided by h. Now, the nice thing here is that all of these things are zeros. Wait, that was supposed to be times h, sorry. All of these terms are zeros except for my h cubed term. So this becomes the limit as h approaches 0 of h cubed over h. This cancels to give me an h squared. Now this is a polynomial in h, so I can find it by evaluation. This becomes 0 squared, which is 0. So the derivative of x cubed at x equals 0 is 0. This is very interesting because think about what x cubed looks like. It looks like this. What this is telling me is that as I go through x equals 0, for one moment there, I am actually facing in a purely horizontal direction. So the x-axis is actually the tangent line to x cubed at this point. Now you might say, oh, but it looks like it's a curve that's cutting through this line. Well, yeah, it's not that tangents can never cut through the curve. It's just that they have to be going in the same direction as you would be going as you walk along this curve. So this time it cuts through, but it's because that's the direction that you're going. In fact, what's happening here is as I come up here, I would be kind of turning towards the right, turning downwards, and at this point I turn towards the left and start turning upwards as I walk along. Okay, so that is really what's happening here, and that's why the tangent looks sort of like it's cutting through. But again, the definition of a tangent isn't whether it cuts through. It's, are we facing in the same direction as a person would face as they walk along this line? All right, so hopefully everybody's okay with that and kind of has an idea of what we're going on with here. Next time, like I said, we'll start talking about the derivative as a function and how we can then use that function to allow us to very quickly answer questions about instantaneous rates of changes and finding tangent lines and all that kind of thing.